Okay, welcome back to the last talk in the morning session. We have Professor Shaunak Dev from IISc Bangalore, and he will speak on Greenberg's question for Siegel modular forms.
So thank you for invitation. Thank the organizers for inviting me here. I'll be talking about Greenberg's question for Siegel modular form. It's a joint work with Bharadwaj Palvanan, who is here, which is great. So if you ask me any question, I'm going to point towards him. The plan is I'll start with some history, then move on to the Siegel modular form case where I have to formulate the question, then some results, maybe then some proofs. I don't know how it's going to go because this is the first time I'm giving this talk. The paper is being written up. All right, so we start with this question. Even though I have said it's the question of Greenberg, it's really the question of Greenberg and Coleman. I think they asked sort of independently, and maybe Coleman had a different formulation. But the question is quite simple. You take a prime P. F is a P ordinary modular eigenform. Of weight greater than or equal to 2. K greater than or equal to 2, and we let rho f be the p-adic Galois representation attached to f. So the question is, if rho f restricted to GQP is a direct sum of two characters, does that mean f has CM or complex multiplication? In other words, the representation rho f itself is induced from a character chi of GK, where K is quadratic imaginary. So if this happens, we say that rho f is split at P. So the question is, if you are split at P, are you CM? Right? Or in terms of Galois representation, if you are abelian at P, are you induced globally? It's kind of a very striking question, because it's sort of telling you what the behavior at 1 prime P, it's sort of dictating something global. Right? For instance, if you know that this happens and the answer to this implication is yes, you know that f can't be of square free level and trivial Nebentipus. See, so it's kind of a sort of a wild question, so to speak. All right, and this has been studied for some time. So I guess the first result is due to Serre, where he proved this implication for elliptic curves. Sorry? That's a good question. I don't know why Greenberg said it was ordinary. I think with Coleman, I think what he said, he conjectured something like if this happens, then it's in the image of some power of theta. And then I guess the ordinariness sort of comes from there, I think. I'm not entirely sure, but at least when it comes to Coleman, the ordinariness. That's also is true. That's true. Okay, that's a better. Yeah, that's a better answer. Right. Right, but it could be a twist of ordinary, but anyway. All right. So as I said, Serre proved the forward direction for elliptic curves, and basically this is known in many weight 2 cases, or in fact parallel weight 2 cases for HMF, or Hilbert modular forms, due to works of Ghate, Emerton, Binzhou. These are sort of individual works, not a collaboration. Then there is this famous result of Ghate and Wetzel. So you have rho f, and you can look at rho f bar, which is the mod P Galois representation attached to rho f, where you just take a stable lattice and you reduce it modulo the uniformizer. So you get, and semi-simplify if necessary. You call it rho f bar. Then what Gate and Wassel proved is that under some mild assumptions on rho f bar, they prove after fixing time level that this implication is true for all but finitely many p ordinary eigenforms G such that rho G lifts rho f bar. So they fix rho f bar, and after fixing the time level, they prove that this implication is indeed true for all but finitely many G, so that the Galois representation is lifting rho f bar. So when you reduce this rho G modulo the maximal ideal, you get rho f bar. Or in other words, what they do is they prove this implication if you replace f by Hida family in the question. So they prove the same statement if you replace f by a Hida family. So if the local representation at Hida family is split, if and only if the Hida family is CM. That's what they prove. Then of course in joint work with Bhaskar, they also extend their result to Hilbert modulo forms of parallel weights. So under more hypothesis, they extend results of Gate and Wassel to Hilbert modulo forms of parallel weight. Right? And then there is, maybe I should go to crossover. And there is also work of Castella, Wang, Erickson. What they do is they prove rho f bar is, they assume first that rho f bar is induced from a residual character. And under some assumptions, maybe I can give one of them. For instance, if you look at the class group of K, modulo P times class group of K, and you look at the component corresponding to psi bar modulo psi bar sigma. Psi bar sigma is like the conjugate character of psi bar. This is 0. This is one of the assumptions. So if you assume this and some more assumptions, they prove that this implication for all p ordinary eigenforms G such that rho G lifts rho f bar, and level of G is tin conductor of rho f bar. Yes, thanks. A quadratic imaginary. No, not all but finitely many. Basically for all lifting rho f bar, but there are lots of assumptions, like this class group assumption and some more assumptions about the conductor of the character. And maybe I should also mention that this result was also proved independently by myself and Gabor Visa, under very slightly weaker hypothesis. And what they do, another thing that they prove is they prove the results of Gate-Wassel after assuming some Iwasawa class group to be finite and some Iwasawa class group to be cyclic. Cyclic as a ZPT module. So they do recover Ghate-Vatsal, but they have these additional assumptions which were not present in the initial work. Okay, a couple of remarks maybe is that Ghate-Vatsal gives this another characterization of CM component, which says that infinitely many weight one points are classical, and they use this Artin representation attached to weight one points modularity lifting theorem to sort of prove their result. On the other hand, Caste and Wang Erickson go via Ribet's method, and that's why they have these additional assumptions, which they can't do without. Okay, so now we'll talk about what this question means for Siegel modular forms. Now, yeah. Oh, I see. It's in the appendix, right? No. Oh, sorry, I had no idea. Yeah, you're right. So maybe. Oh, for real. I see. I see. I see. Abelian variety, I see. So I should add his name here. Thank you. Yeah. Yeah. So the result is done for parallel weights. I think. Yeah. It's there, but I don't think something is done there. I mean, there's some progress in the paper of Bhaskar and Ghate and Vatsal. They do mention this case, but I think they do prove some results towards it, but I don't think they have the exact result that I was saying. Because as I said, their method lies upon these weight one specializations, which have Artin representation. You move away from parallel weight, you don't have that. So that method immediately doesn't work out. Yeah. All right. So what about for Siegel modular forms? Now, as I said, there's slightly more subtlety because with Siegel modular forms, there are four-dimensional representations. So there's more than one splitting possible, right? Here, there was only one splitting possible. So we'll now first fix a setup where splitting will make sense, and there'll be only one kind of splitting. And then we'll ask the same question. Okay, so let's go to setup. I'll recall a form of automorphic induction, which gives you Siegel modular forms. So we let P greater than or equal to 5 be a prime, K be a totally real field, quadratic extension of Q, OK be the ring of integers of K. We assume that P splits in P1, P2. And we let G be P ordinary or P nearly ordinary, depending on how you want to call it, cuspidal, Hilbert modular, new form of over K of level some M, which is an ideal in OK, and weights K1, K2, with K1 greater than or equal to K2, So the weights are indexed by real embeddings of this totally real field K. So I can always choose an embedding so that this holds. I mean, it's just a matter of choice of convention. All right. And we view them over QP bar. We view G over QP bar. So with Hecke eigenvalues over a finite extension of ZP inside QP bar. And if you're wondering what P ordinary means, P ordinary just means that you look at the Pth Hecke operator normalized, and its eigenvalue is a p-adic unit. So perhaps I'll write it. P ordinary means that if you look at T prime P, which is T prime P1 times T prime P2, the normalized Hecke operator, their eigenvalue is a p-adic unit. Oh, I forgot to choose the same parity. All right. Now, if Nebentipus of G is actually a character, or maybe I should say, can be extended to a character of GQ, and if you look at the induction from GK to GQ of rho G, where G is, where this is the p-adic Galois representation attached to G, if this is absolutely irreducible, then there exists a Siegel P ordinary Siegel modular eigenform F of some level gamma, which I'll talk about later, and weights K1 plus K2 by 2 and K1 minus K2 by 2 minus 2. Oh, plus 2, thanks. 2, such that rho F is the induced representation from GK to GQ of rho G, where rho F is the p-adic Galois representation attached to F. So this is like the analog of CM form or automorphic induction in the Siegel modular case. Okay, so we'll call F maybe stable Yoshida lift of G, but I think it's also probably more standard notation is automorphic induction of G. And P ordinary, if you're wondering what P ordinary means, you take the Hecke polynomial, which I won't write, it's a degree 4 polynomial, and roots have certain valuation. So perhaps I should say that P ordinary means if F has weight W1, W2, then Fp ordinary, if Pth Hecke polynomial of F, the polynomial in QP bar, it has, then if the roots, sorry, if the roots of the Pth Hecke polynomial of F have p-adic valuations 0, K1 minus K2 over 2, K1 plus K2 over 2 minus, sorry, I said W and W2, right? So, sorry. 0, W2 minus 2, W1 minus 1, and W1 plus W2 minus. So if this happens, then we call it P ordinary. It's similar to the definition we have for the modular forms. All right, so we have found sort of an analog of CM forms in the Siegel case. So one thing to remember is that if you look at rho F bar, this is from GQ to GL4F, the residual representation, F is the residue field of O, which was sort of the ring of integers which contain Hicke eigenvalues of G. So the representation attached to G takes values in GL2 of O. You induce it, you get something in actually GSP4 of O, and then you reduce it. So this representation actually is in GSP4, but for the moment we put it in GL4. So if you have is the residual representation attached to F, if this is true, then if you look at what is happening locally, is that this is just, you take rho g bar restricted to the local Galois group at P1, and you take rho g bar and you restrict it to local Galois group at P2, where rho g bar is again local residual Galois representation attached to G. Mod P residual Galois representation attached to G. So you see, we have a splitting here. So a natural analog would be that of the question would be that if you have a Siegel modular form of, let's say, cohomological weights, which is lifting this rho f bar, then does locally split mean whether you are an automorphic induction or not? But then again, there is one small hypothesis we want to make for the question to make sense, is because these could have further splittings, and then being split may not be unique. So here comes my first hypothesis, so that then the question would make sense. So I'll just list a bunch of hypotheses here. There's a line of control is back here. So the first hypothesis is neither rho g bar restricted to GKP1 nor rho g bar restricted to GKP2 are split. So both of them are indecomposable. Because of the ordinary hypothesis, we know both of these are reducible representations, but we don't want them to be split. Because of this, now we can sort of phrase our question with no ambiguity. Because of this hypothesis, there's only one way of splitting your local Galois representation. I don't know that. Because I don't know if this whole the theta operator and everything, if that has been formulated in the Siegel case. Okay. Yeah, I don't know. Yeah. Yeah, I mean, true. No. I was just saying that to formulate the question. So because it's a four-dimensional representation, you could be split in many ways. And when I say split, I want just one split to happen, which is 2 plus 2. So this sort of ensures that you can't have more splitting, because if residually you have more splitting, a lift could have more splitting. So that's why I've just put some hypothesis on the mod P representation to begin with. Okay, I'll just formulate the question there. All right, so the question is, suppose H is a P ordinary Siegel modular form with weight K1, K2, with K1 greater than or equal to K2 greater than or equal to 3, and rho H lifts rho F bar which we have sort of fixed in our setup, then if rho h restricted to GQP is a direct sum of V1 direct sum V2, both of them two-dimensional, this is rho h is split at P, then does that mean rho h or h is a stable Yoshida lift? Where rho h basically is induced from some rho g prime from GK to GQ. So this is the question I want to address. And as I said, I just spent some time on the setup and put the hypothesis so that there's no ambiguity about what splitness means. Because otherwise there could be more than one way of splitting, or even if you have splitting into two-dimensional, you might be induced from some other extensions. So just to make sure that everything is working fine, I put some hypothesis. All right, so this now time to present some results, but before that, I need to sort of dump a lot of hypotheses. So I should say that at the first step, I mean, of course, this is the question we are interested in, but at the first step, we would like to know if we can prove analog of Ghate-Vatsal, and then go for each form, because the Ghate-Vatsal is sort of a weaker statement. And to do that, now I have many hypotheses. The first thing is about the level of G. So M, which is level of G, is actually equal to some integer M times OK, where M in Z is a square-free integer with P not dividing M, and G has trivial Nepenthes. Then if I look at the Tay-Martin conductor of rho g bar, that is M, which basically means that rho g bar is ramified at all the primes which are dividing the level. Then some hypothesis on the prime. So if L is a prime dividing the integer M, then P does not divide L power 4 minus 1 times L cube minus 1. If L is ramified in K, then again this congruence condition is there. And an additional condition is there, which says that if you look at trace of rho g bar at frob lambda, where lambda basically LOK is lambda square, it's the prime ideal lying above OK. Oh, I forgot to say that M is also co-prime to discriminant of K. So if I look at trace of rho g bar from lambda square, and I subtract L plus 1 times L power K1 minus 2, this is not 0. In other words, that the primes which are ramified in K are not level raising primes for G. I have two more hypotheses, but I'm getting close to line of control, so maybe I'll just go there. H5 is that rho f bar is absolutely irreducible and has big image. What it means is that roughly SL2F prime cross SL2F prime is inside the image of rho f bar restricted to GK for some F prime, subfield F prime inside F. So this is typically big image is that SL2 is inside for two-dimensional one. And actually, if you look at rho f bar as a representation in GL4, it won't have big image because it is induced. But here big image corresponds to having big image inside GSP4. And finally, rho f bar restricted to GQP, when you take its semi-simplification, it's a sum of 4 characters, and I want it to be the sum of 4 distinct characters. It's a direct sum of 4 distinct characters. All right, so a bunch of hypotheses which we unfortunately need. I'll comment on where all they are used, but these will be in force. I won't now say that assume them. They are now assumed from now on, H1 to H6. Okay, and in this case, the level of F is actually gamma naught of N. So this is a subgroup of SP4 of Z. It consists of matrices A, B, C, D, such that C is 0 mod N. And of course, these are all 2 by 2 matrices. I should, oh, damn it. These are in SP4 of Z. Okay, so the exact formula for N, I think it basically has the same prime factors as that of M times the discriminant, but there might be some squares appearing or something, so I'm not giving the exact formula now. But it is of the Siegel congruence level. Okay? Right? So now I let T be a local component of P ordinary Siegel Hecke algebra or GSP4 Hecke algebra over O of tame level gamma naught of N. So it's generated by all operators away from N and then UP1 and UP2, right? And what we know is that T is a finite integral extension of lambda, which is Iwasawa algebra in 2 variables. These are like the weights. You can think of them as the weights of the Siegel modular form. All right. So we have this. We know T is torsion free, but freeness is tricky. Freeness is not always known, and we need freeness in our results. So yeah. I should confess that I don't work in Hida theory at all. I'm on the Galois side always. So I'm always hesitant as to, but thanks. Yes. I'm trying to, yeah, I'm trying to enter the family. All right. So as I was saying, that the torsion freeness is not good enough for somehow our method of proof. We need something like freeness. And the remedy for that is an R is equal to T theorem, or a remedy. I don't know if it's the remedy. So that's why I'm going to sort of state that as my first theorem, which is, and that may actually explain a lot of the hypotheses that we have. So to set up that R is equal to T theorem, there exists a representation, okay, I have time, rho T from GQS to GSP4 T, lifting rho F bar, which is from GQS to GSP4 of F. S is the set of primes, dividing N P infinity. So as I said, under a suitable basis, rho F bar actually takes values in GSP4 of F, and you can get a lift of that to GSP4 of T. So of course, this means that you're going to get a map from a deformation ring to T. But what is that deformation ring? It's the minimal ordinary deformation ring of rho f bar. So what's minimal ordinary? Maybe I'll not formally define it. I'll just say our minimal ordinary is ring interpolating deformations rho from GQS to GSP4 of S, where S is a complete local Noetherian ring with F as, or maybe Artinian ring, and then I'll say it's pro-representable with residue field F, such that you restrict it to GQP, you have this upper triangular shape after change of basis with chi4 unramified. This is the ordinary part. Now we come to minimal part. Rho of IL under a suitable basis is generated by this unipotent matrix if L divides M, which was the level of Hilbert modular form, and rho restricted to IL is generated by this diagonal matrix 1, 1, minus 1, minus 1 if L ramifies in K. So this is like the universal minimal ordinary deformation ring of rho f bar. All right. So the first theorem we have is psi t is an isomorphism and T is free over lambda. So if you're familiar with the literature, this is the analog of theorems of Genestier-Tillowin and Piloni, and we use the same method, and that's why a bunch of hypotheses are there. Just one small comment. If I'm saying that this ring is giving me a map onto T because of this deformation, that means this deformation should be satisfying all these three properties. And we are not able to use local Langlands here. So because of that, we just prove these properties by hand. And to know these properties, we need H2 to H4. The hypotheses from H2 to H4 are required to get these shapes for rho t. Yeah. This one? But this is in the H0 case, and the only reference I saw was Piloni, where he doesn't consider this case. He considers sim cube and big image, right? Yeah, and with Klingen levels, where we are in Siegel congruence levels. All right, so this is theorem 1 that we prove. And now we are ready to state the actual theorems that we wanted to prove. But before that, I need some more notation. Right. All right, as I said, and this was proven by Piloni in many cases and also by Genestier-Tillowin. But I think Genestier-Tillowin is in H3, this is in H0. It's a bit of technicalities, yeah. Yeah. Yeah, and also I think Tillowin proved it for the. And there's also a theorem of Tillowin for the nearly ordinary. Yeah. Right. So now to state the other theorem, as I said, I need some more notation. So we let P be a minimal prime of T. And we say that the component corresponding to P is Yoshida if all classical specializations of T mod P are stable Yoshida lifts. Like a CM component, an analog of CM component. And then, maybe I write here, I write T Yoshida to be basically just T modulo intersection of primes P, where P is a Yoshida component. The intersection is over Yoshida components. And from theorem 1, or you can always sort of take a Hida family and try to automorphically induce. But using some arguments, you know that this intersection makes sense, like the Yoshida components is non-empty. The number of Yoshida component is not zero. So therefore, this makes sense. So then, if you look at this representation I have to GL to T, GSP4T, then you compose it with GSP4T Yoshida, and you call it maybe rho Yoshida. And then this representation is actually induced from a representation of GK. Tau is from GK to GL2 of Yoshida, because we are only considering Yoshida components where at all classical points it is induced. So we have that. Then we let V be form T comma T conjugate, where T conjugate is a representation of G, such that T conjugate of G is T CGC inverse for any C in GQ minus GK. All right. So this is a representation of GK over T Yoshida. And I define a Selmer, a discrete Selmer, of taking values in the, so it's a Selmer of V tensor with the quadratic dual of T Yoshida, which is kernel from, it's basically fine Selmer. So you take kernel from T Yoshida, V tensor T Yoshida dual to H1 of GK P1 cross H1 of GKP2. So it's trivial at all primes above P. And it's unramified at all other primes. Lambda in S minus P1, P2. It's I lambda V tensor T Yoshida dual. Yeah, I hope all the brackets are matching. Yeah. So this is the Selmer I'm going to consider. As I said, it's like a fine Selmer for this, except that I'm sort of taking values in the quadratic dual. Right. Now, after notation dump, I'm ready to state the second result. Perhaps I'll just combine the next two results I want to state in one. Let's see. Here, two. So of course, as I said, for R is equal to T theorem and for also for this, those hypotheses H1 to H6 are in force. And we suppose that this Pontryagin dual of the Selmer I just defined, it's pseudo-null, which means that if you localize it at any height 1 prime of T Yoshida, you get 0. And so in this case, if T is not isomorphic to T Yoshida, yeah. Oh, no, that's definition. Sorry. Yeah, it's like a notation. The theorem ends there. Yeah, exactly. Exactly. So if T is not T Yoshida, then there exists a minimal prime P inside T such that when you reduce this representation modulo P restricted to GQP, this is not split. Or in colloquial languages, maybe if there exists a non-Yoshida component, then there exists a non-split component. Right? So this was sort of our first step towards seeing Ghate-Wetzel. And then we have a slightly better statement, but with stronger hypothesis, which I'll state now, which perhaps I'll just let go of the hypothesis. Yeah. No, I don't know actually, unfortunately. Yeah. But it's like the same hypothesis that Kasteyev and Ericsson have, where they assume that some Iwasawa class group is finite. It's basically being pseudo-null. T Yoshida is yes, because it will come from basically Hida algebras for the totally real, the nearly ordinary Hida algebras for totally real field. So it will be flat over lambda, flat and free. Theorem 3. So we again assume that the same Selmer group is pseudo-null and cyclic as T Yoshida module. I hope this is the correct hypothesis. Okay, then, and we let P be a minimal prime. Then rho T modulo P restricted to GQP, it's split if and only if the irreducible component of T corresponding to P, this is Yoshida. This is the analog of Ghate-Wetzel, where where under this stronger cyclicity hypothesis and of course pseudo-nullity, we prove that component representation is split if and only if you're Yoshida. So a couple of comments, as I was saying, that Kastayev and Ericsson have the same sort of hypothesis, except that now they are in this in the ZPT case, so they have finiteness instead of pseudo-null, and cyclicity is also there. All right. Yeah. Oh, the slight silver lining is that for theorem 3, we don't need all those hypotheses. Basically, for theorem 3, we don't know R is equal to T. So because of that, a bunch of hypotheses just get cut down. So even though the cyclicity assumption has been added, some other assumptions have been subtracted. Not all H1 to H6 removed, because we do need H1, and then the G square free and all those things are there. But you know, that big image and those things, I don't think we need it. Yeah, basically we don't need theorem 1 for, we need theorem 1 for theorem 2, but not for theorem 3. Okay, I have like 10 minutes. Just have a sip of water and see if anybody has any questions. Mm-hmm. Mm-hmm. Right. Yeah. Mm-hmm.
Then the quotient has to be intersection non-minimum.
Yeah. So yeah. So I mean, yeah, you're right that maybe all Yoshida. Yeah. What I wanted to say was that I think I'm just taking the intersection over Yoshida primes, but yeah, if I want to sort of get the non-split extension, then I think I need more primes. But here I'm just looking at the components and not these other non-minimal primes which might come in.
Then the thing called easier.
Yeah.
And R equals T of your thing
Mm-hmm.
doesn't compare. We can't say.
Yeah, but I mean, I was sort of defining T Yoshida to be this.
Then yeah, even find that way.
Uh-huh.
I'm saying that this may not be.
This may not be flat. Okay, I need to.
It does reflect the deformation.
Yeah. So yeah. You're right. Yeah. So you're saying that I can take nearly ordinary deformation ring, and because of the induced on the GL2 side, and if I induce it, I get a map from R to that R, and you're saying that R might not be. No, but this R is. Yeah.
He's only considering parallels, not considering exceptional points which may not exceptional Yoshida that may not lie in Yoshida family.
Yeah, but there could be a non-cross, how do you say, transcendental Yoshida. It's just a singularity of the crossing on.
Right, but he's not considering those points.
Yeah,
But
then you need to have a quality. You need to consider that point.
yeah. But yeah, you're right. Then some freeness might be an issue, but all we need is this is torsion free. So yeah. So which is all we sort of need. Yeah. All right. So I'll say something about the proofs. I only have 5 minutes. Everyone is hungry, so I don't want to go over time. Right. So the R is equal to T theorem is just, you go to fixed weights and you apply Taylor-Wiles. This has been done in Geneste-Tilveen and in Piloni, and we just follow that. We just have to check big image hypothesis and various things that I said, and then you just patch it up to get R is equal to T theorem. So it's really like what has been done in the literature. Proof theorem 2, perhaps I'll try to give a quick sketch of theorem 2. We use basically Ribet's method. So the starting point is that under suitable basis, I need to get this right. If you look at the group algebra, of the representation restricted to GKS, it looks like, that's the buzzer, looks like M2T, M2B, and M2T, where B inside T is an ideal. It's a GMA if you're familiar with that language. Okay, maybe I'll just erase this part. So the first thing that we prove is that this B is actually equal to J. It is the kernel from T to T Yoshida, which I had defined. And so that would mean that B is not zero, because we are assuming that there is at least one non-Yoshida component. To prove this, the statement basically becomes that if your Galois representation attached to F is induced from a two-dimensional representation, then that two-dimensional representation is actually Hilbert modular, which you can use theorems of Skinner-Wiles and Kissin to do it. Then Ribet's method is going to tell you that J mod J square, which is same as B times J mod B, there's a surjection onto this module from the Selmer group we have. There's a surjection like this, which means J mod J square is pseudo null. Then one observation is that you look at, it's not observation, it's the fact that if you look at the zeroth fitting ideal of J, it is contained inside the annihilator of J, which means that the zeroth fitting ideal of J mod J square, now this is a T Yoshida module. This is contained in the ideal of T Yoshida, generated by annihilator of J. Right? But now, if you look at J is the kernel of this map. This is free. This is torsion free. So we have that J is reflexive. And the another thing that we know is that this lambda injects into T modulo the annihilator of J inside T, and J also injects into this, because we have a reduced Hicke algebra, which means sorry, I'm all over the place, but so that means that lambda modulo lambda intersection J, now J and lambda are inside T modulo annihilator of J. They go inside T modulo annihilator of J, comma J. But now lambda is reflexive, J is reflexive, so you get lambda intersection J is reflexive, and so it becomes principal. So which means that fitting ideal of J mod J square is now contained in some height 1 prime of T Yoshida. And because of this, you localize at this, you call this prime V at P, you localize at this P, you become non-zero, which is a contradiction because you have assumed that it's pseudo null. And that's why we get that, we get a contradiction. But sorry, I forgot to mention the hypothesis. The hypothesis was you are split everywhere. So I went a bit too fast. So I should have said that suppose rho T is split. Well, only then Ribet's method gives me this morphism, and I get a contradiction to this hypothesis. Sorry, I went a bit too fast because I was pressed for time. And yeah, I guess I'll stop here maybe, but one thing I'll say is that theorem 3 is a similar proof, but now because your principle, the commutative algebra is much easier. You don't necessarily need reflexivity or anything. And so the same argument sort of works nicely. You have to just replace T by T decomposable or something like that, but you don't need this reflexivity and all. And if you see, we needed the reflexivity because of which we proved T is free. So that's sort of the only reason where we needed T to be free. So the result would hold if we assume that T is free, except that we didn't know how to do it except R is equal to T theorem. All right, it's time. I'll stop. Thank you.
More questions?
Yeah. Yes, the same one. J intersection lambda is reflexive because J is reflexive lambda module, and lambda is that. So if you look at the J is reflexive because it's kernel from a free lambda module to a torsion free lambda module. No, it is two-dimensional. Oh, sorry, yeah.
That criteria still works, I think. If it's torsion free and T is free, I think the torsion.
Yeah. Oh, you mean crude dimension 3? Yeah, they are crude dimension 3. Yeah, 3. Yeah. But the criteria is the reflexivity is still hold, like the
J needn't be free, but it's
reflexive. Yeah. Mm-hmm. Yeah. So yeah, that's a good question. I'll confess that we have only started thinking about this, and really, I don't think this kind of problems were formulated earlier beyond GL2, even though they are not. I mean, they are natural to formulate, but yeah, short answer is I don't know. I'd like to think about it, but we haven't really thought about it.
So I think the other things maybe consider as sim cube of F and maybe induction from Bianchi things, but I think those don't interpolate in two variable families. That's why we didn't consider. So we are essentially looking at analogs of Gate-Wetzel, which means we want to look at Hida families. Right. So what I'm saying is that the other inductions like sim cube and inductions of Bianchi forms don't enter this picture because you can't form two variable families.
I mean, the question can be formulated. You're right that the question can be formulated, like the individual question that I formulate. Like you can formulate a question like that, but except that if you want to go via this family root, the family root is not amenable to these other like sim cube or induction from a Bianchi modular form because just the families aren't there. But you're right that the question could be formulated, but yeah, we have to think about it. Yeah. Yeah, exactly. Yeah, so that's when you have more than one splitting, right? Because right, but it'd be 2 plus 2, is it? Because I thought you'll get direct sum of 4 characters when you, yeah. That's true, yeah. Then it should be, that's an interesting. Yeah, we haven't, as I said, we are still exploring. So this is like the first case, but that's a good point. We were thinking about it, but we thought maybe that this is the good starting point. But you're right. Maybe if you're keeping track of the weights, then I think you're right that exactly. Then the splitting will be splitting will be of some form. And yeah, there's one more thing I forgot to mention is that the Gate-Wetzel have this weight one, the characterization using weight one specializations. We're trying something similar, and we have some sort of a characterization using weight k, 2 Dirham points. But I didn't have time to mention, and we're still writing it up. So,
Anybody else? Okay, so let's thank Shaunak and all the speakers for following us.